Hey guys, Mr. Palmer here with a Ka calculation problem. I'm looking at weak acid equilibrium. This is a great one for AP Chem. Take a look at the problem. I would say give it a try and see how far you can get, and then go back through it and watch the explanation. This is one pretty simple. We're looking at lactic acid as a weak acid. You're given the Ka. You're given the mass of acid and the volume, so it's going to ask you to find a concentration. You are given the equation, and you're going to have to find the equilibrium expression as well, and so we're going to have to do part of that ice calculation. So as I said, give this a try, and then we'll get through it, okay? So here we go. For the first part, part A, we're looking at an equilibrium, right? We're looking for a Ka, and you're given a balanced chemical equation. So for part A, it's just asking you to write an equilibrium expression. So for an equilibrium expression, for an acid dissociation, you're going to have the weak acid right in here, right? Plus water gives you your conjugate base, and it's going to give you hydronium, right? That's what's making it an acid. And the equilibrium expression, the Ka, is the products over the reactants raised to the power of their coefficient. You'll note that the water is missing, right? There's no water in this because the water here is a liquid, and you're not going to show that. So the typical Ka expression has hydronium here times the conjugate base over the original acid, okay? So I'd say that's like a 1-point question, just being able to write that expression. Part B asks you to calculate the initial concentration of the acid. Now this doesn't have to do with equilibrium or Ka. This is just being able to do a concentration problem. You're given a mass of 120 grams of the lactic acid. It's HC3H5O3. So you're going to have to turn that into moles, right? Because we're looking for a molarity. And that's going to be the molar mass. We're going to add that up. It's 90.02, I think, or 90.09 grams per mole. That gives you 1.332 moles. And molarity is moles over liters. 1.332 moles. And the volume it gives you in the problem, I believe, is 2.00 liters. So we're going to come out with a concentration of 0.666 molar, right? So there's the initial concentration of our acid. It's just a concentration problem. For part C, you're going to be asked to calculate the concentration of the conjugate base at equilibrium. So I rewrote the expression here. So here is our balanced chemical equation. Here is our equilibrium expression right here. And so for a weak acid problem, we're going to be doing ice because this is equilibrium, right? We want the initial, the change, and what's it going to be at equilibrium, right? That's what our ice problem is. So if we go back in the last part, we found that this initial concentration of the acid is 0.666 molar. The water, we're not going to worry about. We're not looking at the concentration of water. It's not in the expression. And both of these were 0, right? The hydronium and the conjugate base. We are going to put in the change. Obviously, this is going to shift to make some of the reactants at equilibrium. So the acid is going to go down. Some of it's going to react with the water. And looking at the 1:1:1 ratio, if the acid goes down by X, the conjugate base must go up by X, as will the hydronium ion. So we're going to say that this is 0.666 minus X, X, and X. And we're going to substitute these values into the equilibrium expression, right? So we already know what the Ka is. It's given to you in the beginning of the problem, in the prompt. And that is that Ka value is 1.38 times 10 to the negative fifth. That is equal to, okay, we're going to substitute in the hydronium, which was X, and the conjugate base, which was X. And we're going to put that over, right, our acid, which was 0.666 minus X. Now, if you're trying to solve this problem, you're going to see that it's going to give you a quadratic. We're going to wind up with X squared on top, right? That's going to be X squared. And on the bottom, we're going to have 0.666 minus X equal to some number. So We don't really want to do that. And so they're going to find an easier way. If you don't want to use the quadratic equation, which you could also just take this part on the bottom, and we can kind of say that because the k is so small, that this is roughly equal to 0.666. Okay? It's equivalent to. That x is going to be such a tiny number. So we're essentially assuming that's going to be a 0. And what we do is a method of successive approximation. And so we set that to 0, so we're going to get 1.38 times 10 to the negative 5th equals x squared over 0.666. And you're going to solve for x. When you do that, you come out with a number of 0.00303, which is 3.03 times 10 to the negative third is going to be your x value. Now, is that okay to do? Can we assume that that x is 0? Well, a quick way to do that is to check the 5% rule. You take this x value and you put it over the 0.666 and check to see what the actual percent dissociation is. And that's what we're going to look at really in the next two parts. So I'm going to stop there. This is how we find our x. And in part 2, I'll come back and talk about the pH and the percent dissociation. So this x value is going to be our concentration of the conjugate base in this part. And I'll be back with the rest in the next part 2.